that study with us. Professor will talk about the Jones Polynomial, Khovanov Homology from gauge theory.
Thank you. So I'm only using one screen, so keep the blackboard free. So I hope you're all at an angle where you can see it. That goes for you, Nikita. Don't sit at the very end. Move in somewhere. Okay. So I'll be talking about an approach to Khovanov homology and the Jones polynomial via gauge theory. But today I won't try to describe where this approach came from or why I think it's true. That's actually more or less what I did a few years ago in another lecture at the Simon Center. On that matter, all I'll say is that the starting point is similar to what was the starting point of Gukov, Schwartz, and Waffe, who were following Ugry and Waffe. My approach differs mainly in that I try to express everything in terms of gauge theory, partly because I wanted to understand the relationship to the usual gauge theory approach to the Jones polynomial via Chern-Simons theory. But also I wanted 3- and 4-dimensional topological invariants to be manifest rather than being verified by checking generators and relations. And to do that, I developed an A model, whereas most approaches involve mirror B models and are very efficient for calculating, but do not lead to manifest symmetry. Now, so as I say, I'm not explaining. There are a lot of things I'm not explaining, and some of those things are in previous talks that were written up and which you can find on the web. I'll start by describing the Jones polynomial, because as you'll see, the point is that from the point of view that I'll use in describing the Jones polynomial, the extension to Khovanov homology follows from some lucky facts, some simple but lucky facts. The Jones polynomial will be computed by counting solutions of certain elliptic partial differential equations that people sometimes call the KW equations. They came up in my work with Kapustin on gauge theory and geometric Langlands. The equations are 4-dimensional equations that are somewhat like the Hitchin equations in 2 dimensions. So we pick a compact gauge group G and an oriented Riemannian 4-manifold M. The equations will be equations for a pair. If you sit down quickly and look at the slide, you haven't missed anything. Okay. Just read that page. I didn't say anything previously. So we pick a compact gauge group and an oriented Riemannian 4-manifold M. And we write equations for a pair A and phi, where A is a connection on a G bundle over M, and phi is a 1 form valued in the corresponding adjoint bundle. And here are the equations. And I've just written them down so that you can see that they're very explicit, manifestly invariant PDEs. They can be generalized to depend on a real parameter t, but we'll only get to that later. And they're elliptic equations modular the gauge group, so it makes sense to try to count their solutions. We'll consider these equations in general in any 4-manifold, but for the application to knots, the 4-manifold will usually be W times R plus, where W is a 3-manifold that might contain a knot, and R plus is a half-line. Hi. Now I'm not sure what to do because you've come in 1 minute too late. Now you will be confused. So we're studying these equations for a pair, a gauge field and a 1 form valued in the adjoint bundle. You don't have to know a lot about them, but they exist. They're elliptic partial differential equations. And we'll study them on a 4-manifold that's the product of a 3-manifold times a half-line, where the knot will be in the 3-manifold. So the half-line will be parameterized by a variable y, which is non-negative. So I've drawn the picture here. W is the 3-manifold. The half-line goes off to infinity. And there might be a knot in W. So we could develop the theory for any W, and it makes sense. But if we want to get it's most simple to understand the relation to the standard quantum invariants of knots, such as the Jones polynomial, if W is just R3 or S3. If W is something else, we'll have to work harder to understand exactly how the invariants we get are related to more familiar ones. Now, we need to discuss our elliptic PDEs on this space. We need boundary conditions. And as y goes to infinity, I'll just ask that everything goes to 0. But at y going to 0, there's a subtle boundary condition that's one of the main points of the theory. In fact, the reason that I'm not really going to tell you today why I think the story is true is that I wanted to have time to properly explain the boundary conditions, which there isn't time for if I give the other talk. So describing the boundary condition will be my main goal for today, though I will still spend about 15 minutes explaining what the boundary condition is used for. So although it's my main goal to explain the boundary condition, for now I just make a couple of remarks. So first of all, the boundary condition will depend on the knot K, and it will depend on a labeling of K, or more generally, a labeling of each component of a link L by a representation that I'll call RV, R-check, of the Langlands or Giannold dual group, which I guess people read G-check. So if you want to do the quantum knot invariance of a Lie group, that Lie group will be what I'll call this one, and we'll be studying the equations I wrote for the dual group. The only place that K enters the setup is in the boundary conditions, so it's certainly important to tell you about the boundary conditions. So the boundary condition is an elliptic boundary condition, but a rather subtle one. Elliptic means that although the definition is completely different, the resulting properties are similar to what you would get with more familiar elliptic boundary conditions like Dirichlet or Neumann. For example, on a compact manifold, we're not on a compact manifold because we have a half line. But just to orient you, if we were on a compact manifold with boundary, but with this boundary condition, then the linearization of the equation will give a Fredholm operator with a discrete spectrum. So that's an example, but although the boundary condition is unusual, it has all the general properties of standard boundary conditions. With this boundary condition, the restriction to the boundary of the bundle E and the connection A are specified. I didn't say they're trivialized, I said they're specified. As a result, you can define a second Chern class. Well, first of all, I call it second Chern class, but that terminology is really for SUN or UN. So there's an analogous quadratic Casimir operator for any simple Lie group. So there is such a characteristic class, but it's loose language to call it the second Chern class. But we're on a manifold with boundary that, moreover, is not compact. So you have to ask whether it's defined as a topological invariant. Well, I trivialized the bundle at infinity by saying that the connection was 0 there. And at the finite boundary, I didn't trivialize the bundle, but I specified it. So that means that n is defined as a topological invariant, but it takes values not in Z, but in a Z torsor associated to how the bundle was specified on the boundary. That means that different fields that satisfy the boundary conditions will have the property that this integral differs by an integer. The offset from an integer will depend on exactly what there is on the boundary. So torsor means that n isn't an integer, but the value of n mod Z depends only on the boundary conditions and not on the specific gauge field that satisfies them. You could trivialize the torsor and make n an integer by picking framings of W and K. And if you do that, you essentially will recover the standard framing behavior of the usual quantum knot invariants. So the torsor comes in because the boundary condition specifies the restriction of E to the boundary as a bundle with connection, but does not trivialize it. Now, when you have an elliptic differential equation, you can, with good boundary conditions and some compactness properties, you can count its solutions. You don't literally count the solutions. You weight the solution with a natural sign, which for physicists is the sign of a fermion determinant. This sign was important in Donaldson's theory of four manifolds. Donaldson counted instanton solutions on a four manifold, roughly speaking, but he counted them weighted with signs. And all similar theories, there's an analogous sign that comes in. So by A sub n, I mean the number of solutions of the KW equations with second Chern class n. But when I say the number, it should perhaps be in quotes. It's the number weighted by signs. And then you define a polynomial whose, well, you define this series sum of q to the n times a sub n, the number of solutions. So it's a function of q. It depends on the knot and the representation of the dual group. So compactness of the solutions will mean that there are only finitely many terms in the sum. So this is a Laurent polynomial. Actually, it's offset from a Laurent polynomial by a power of q, because we were in a torso, remember? So n is not really z-valued. It's offset from z by something that depends on the details of the setup. So with a slightly unnatural trivialization, you make n an integer. And then this is exactly as I said. For example, if G is SO3, and R check is the two-dimensional representation of the dual group, which then is SU2, this is supposed to be the Jones polynomial. Now, given suitable compactness properties, the counting of solutions of an elliptic PDE is invariant under continuous deformations of parameters. In this problem, the parameters we want to continuously vary, would be the embedding of the knot in S3 or R3. So the statement that the counting of solutions is a topological invariant accounts for the topological invariance of the knot polynomials, given this characterization of them. Now, with this characterization of the knot polynomials, we can explain how to categorify them and find vector spaces, curly h, that depends on the knot k and the representation, and that has a bigrading. I wrote z times z action, but that's a loose way of speaking. I should have said z times z grading, but that also is loose because one of the z gradings is really a z torsor, as I said. But roughly speaking, the vector space has a z times z grading. And then dually, there are generators. If you want to say there's an action, it's a u1 times u1 action generated by f and h, where you could call f fermion number, and h is essentially the second Chern class. And then the knot polynomial is the sort of Euler characteristic or Lefschetz number of this cohomology theory. So the first z grading defined by f is cohomological, and it's shifted by 1 by the differential that we'll eventually have. Oh, sorry. Okay. And the second, h will be the cohomology of some complex, which will have a differential that shifts f by 1 and commutes with h. So we can actually compute this trace either in the cohomology, which is the way I defined it here, or in the underlying complex. The second z grading is associated to the second Chern class. As I keep explaining, the second z grading is not quite a z grading. Now, the interpretation we will use of what categorification means is that to categorify a d-dimensional theory means to derive it from a theory in d plus 1 dimensions in the following sense. A d plus 1 dimensional theory does something for any d plus 1 manifold, or structures in a d plus 1 manifold. But here we will specialize to d plus 1 manifolds that happen to be of the form of a d manifold times a circle. And specialized in this way, a d plus 1 dimensional theory reduces to a d-dimensional theory. So there's not any guarantee that a given d-dimensional theory can be obtained in that way from a d plus 1 dimensional theory, but you can always go down. Given a theory in d plus 1 dimensions, you can always produce a theory in d dimensions. So categorifying means trying to derive a theory in d dimensions from a theory in d plus 1 dimensions. In the present case, the problem of counting solutions of the KW equations on a general form manifold cannot be categorified, as far as I know. But if the form manifold is the product of a 3 manifold and a 1 manifold, and we will take the 1 manifold to be R+, then categorification proceeds as follows. On such a form manifold, it's straightforward to show that the KW equations are the equations for a critical point of a certain functional. The details of that functional are not important in this lecture, but I want to make clear that it's a concrete thing I can write down, so I've written it down. But I have to then explain it. So first, I combine the connection in the one form to a complex valued connection that you can think of as a connection on the complexification of the G bundle E. And then a complex valued connection has a corresponding complex Chern-Simons 3 form. We've taken its imaginary part, and we multiplied by dy. Oh, sorry. So we took M4 to be W, which is a 3 manifold times R plus, but R plus is parameterized by Y. So dy is a 1 form that we wedge with the Chern-Simons 3 form, or rather its imaginary part, so we can integrate it. And there's another term. Oh, sorry. Well, okay. So phi is a 1 form. We take the part of phi that's sort of restricted to W and do the Hodge star in the 3-dimensional sense that converts phi to a 2 form. So star 3 of phi is a 2 form, which is wedged with f and then integrated. So I don't want to explain it more fully because we won't really use the formula, but there is a formula with the property that the KW equations on this kind of form manifold are the equations for a critical point. Now, that means that you can imitate Morse theory and fluor cohomology. So the real point that enables categorification is the following. Put a metric on the space of pairs A and phi. There's an obvious Riemannian metric on the infinite dimensional space of fields, just given by the L2 norm of a 1 form. Introduce a 5th dimension, which we'll call time, and I'll call it t, and write the gradient flow equation of Morse theory for the pair A and phi, where to write a gradient flow equation we need a metric, so we take this one, and gamma was defined on the previous page. So if you're given any functional, you can always write an equation like that in one more dimension, but generically nothing good will happen. Specifically, what won't happen that one would like generically is would be for this equation to be an elliptic equation. The first bit of magic in this problem is that the gradient flow equation is actually an elliptic partial differential equation, so it makes sense to count its solutions, just as it made sense in 4 dimensions. So this is an elliptic differential equation modulo the gauge group, so we can imitate Fluor's definition of fluor cohomology. We define a z times z graded complex theta as follows. Let S be the set of solutions of the KW equations that obey the boundary conditions. For each I in S, we declare that theta has a basis vector psi sub I of bi degree PQ, where P is the eta invariant. Well, L is the linearization of the KW equations. You have the KW equations, you linearize them to get a linear differential operator L. And then eta is the eta invariant of the linear operator L. And in this even dimensional situation, you can show that eta is an integer. So the eta invariant is an integer p, and q is the second Chern class. So that gives a bi-grading of the basis vectors. A differential d acting on the complex is defined as follows. As I said before, it will map bi degree pq to bi degree p plus 1q. Let psi I be a basis vector of degree pq. Then the differential acting on psi I will be the sum over all basis vectors corresponding to solutions of degree p plus 1q with coefficients nij, where nij is computed as follows. This is a very schematic picture in which I've only drawn one direction, which is time. In the past, we started at solution I. In the future, we're supposed to end at solution j. We count the solutions. Well, sorry. We look at solutions of the 5-dimensional equations that start at I and end at j. the solutions will always come in families of at least one parameter, because the equation is invariant under time translations. So what you count are not solutions, but one-parameter families of solutions. There's a natural way to define a sign for a one-parameter family, and the counting of one-parameter families with signs gives an integer nij. So this is something I've told you. As is usual in this type of field, such solutions always have at least one parameter associated to shifts of the time, and what one counts are the one-parameter families of solutions. So by counting one-parameter families of solutions, one obtains the differential acting on this complex. And standard arguments of Moore's theory and Floer cohomology show that d squared is 0. Well, they show this somewhat formally. So from a mathematical point of view, there are analytic details that aren't all straightened out. And when I'm telling you about the boundary conditions, that'll aim at helping you understand better what the problem would be. Now, if G is a symplectic group or a symplectic group divided by Z2, for example, if G is SO3, which is SP2 over Z2, then there actually are two variants of this construction. That's because pi4 of G is Z2 for such G. So a G bundle over a 5 manifold, which in our case is R times M4. Remember, we introduced a new time direction parameterized by R. So our 5 manifold is R times M4. M4 was W times R plus. But in general, a G bundle over a 5 manifold has a characteristic class valued in Z2. I'll think of Z2 multiplicatively, so I'll write the characteristic class as -1 to the nu. Well, nu is an additive representation, and -1 to the nu is multiplicative. In what we did before, when we consider flows, what's flowing is a pair A and phi on a 4 manifold, building up a solution on the 5 manifold M5. This solution has the Z2 valued invariant -1 to the nu. And we can define a second differential, d prime, by modifying the counting, we're including for each flow an extra factor of -1 to the nu. And because -1 to the nu is a characteristic class, which is additive and gluing, this preserves the fact that d squared is 0. So this gives a second differential if G is of the type SP2n or SP2n over Z2. I expect it corresponds to odd Khovanov homology, which is known to exist for what's usually called SU2, but in my language that's SO3. What's usually called Khovanov homology of SU2. The SU2 is the group of the knot invariants, the quantum knot invariants. We're discussing a dual version. So what would usually be called SU2 is SO3 in my language here. But anyway, SO3 is SP2 over Z2, so in that case there are these two versions of the theory, and I expect them to correspond to even and odd Khovanov homology. Now there's one more very important property. I mentioned already one lucky fact about the flow equation, which is that it magically turns out to be elliptic, which is definitely not something we would get if we start with a random functional in d dimensions and write a gradient flow equation in d plus 1 dimension. You can try it, and you won't get an elliptic equation unless you plan very, very carefully. In fact, you'll have a lot of trouble finding a new example of any kind, I think. There are 2 or 3 examples known. But it has another very nice property, which is that it has a 4-dimensional symmetry on R times W. That's different from the original 4-dimensional theory of the KW equations. We started on a 4 manifold with equations that had manifest 4-dimensional symmetry. They were these equations that I wrote in a manifestly invariant form at the beginning. But we broke that symmetry when we defined gamma, and as I said, that's why we cannot categorify the space of solutions of the KW equations on an arbitrary 4 manifold. But after breaking the 4-dimensional symmetry, we added a 5th dimension, and something funny happens, which is that there's a new 4-dimensional symmetry that relates W now not to R plus but to R. So actually the 5D equations, which are sometimes called the HW equations, can be defined on x times I, where x is any oriented 4 manifold and I is a 1 manifold, which for us will be R plus. So also, okay, so that's one thing that happens. We could generalize it from R times W, from a knot that lives in R times W to a knot that lives in a general oriented 4 manifold X. But even before that, I should have said that when we added the 5th dimension, the trivial thing to do was let the knot just sit there at all times. And if it does that, it sweeps out a 2 manifold in the boundary. When the boundary is lifted from 3 to 4 dimensions, the knot will be lifted from 1 to 2 dimensions. So the knot became a 2 manifold sigma in R times W. But in the time-independent case, sigma is just the original knot times R. But the appropriate boundary conditions can be defined for any embedded 2 manifold sigma in X. So the general picture involves an oriented 4 manifold X with an embedded 2 manifold sigma labeled by a representation of the dual group. So I've drawn the picture here schematically. X is a 4 manifold, and it's the boundary of a 5 manifold. And there's an embedded Riemann surface in X labeled by a representation of the dual group. Now, to define the morphisms of Khovanov homology, one considers the special case in which W is R3 or S3, and sigma is asymptotically time-independent in the past and future. But it could be anything in between. For example, to define a morphism from an unknot to 2 unlinked unknots, an example of a possible sigma would be the following. So sigma, time is running vertically here. In the past, sigma is time-independent. It's a single unknot times time. In the future, it's time-independent, but it's 2 unknots times time. And we picked a sigma that interpolates between this and that. But any such sigma could have been incorporated in our story. And the counting of solutions with the boundary conditions defined by such a sigma would give us a morphism from the candidate for Khovanov homology in the past to the corresponding candidate in the future. Now, everything I've said so far, I've said in much more detail on other occasions. And you could find it written up in the talks that, there are a couple of, at the beginning I gave references to talks I've given that were written up. The reason I've been rather brief is that I want to explain the boundary conditions in more detail than time would have allowed if we'd been thorough on this stuff. The boundary conditions have been studied in a paper I wrote with Rafe Mazio, where we showed that the boundary condition is elliptic in the absence of a knot. And we're working on a paper in progress on the case with a knot, and I'll tell a little bit about that case later. I will carry out the discussion in 4 dimensions since going to 5 does not change much. In our paper, we showed that the extension to 5 dimensions was trivial. That once we had written down what we had to know that to show that the boundary condition was elliptic in 4 dimensions, it was trivial that it was true in 5 dimensions. If you ask again later on, I'll explain why that was true. Or if I remember, I'll do it without being asked. The boundary condition is not a simple Dirichlet or Neumann boundary condition. It's defined by saying what fields or derivatives of fields vanish. Sorry, it's not defined by saying what vanishes along the boundary. Those are the more familiar boundary conditions. Rather, the boundary condition is defined by specifying a model solution of the KW equations that has a singularity along the boundary, and saying one only wants to allow solutions of the equation that are asymptotic along the boundary to this singularity. So that's a key sentence. This is going to be the strategy for defining the boundary condition. We'll say what we want a solution to do along the boundary, and there will be a singularity along the boundary. We will declare we like that singularity, and we want to study only solutions that have that same singularity on the boundary. The model solution is a solution on R3 times R plus, where I parameterize R3 by x1, x2, and x3, and R plus by y. There's a simple exact solution where A is 0, and phi is what I've written, where the t's are just constant elements of the Lie algebra of G that obey the SU2 commutation relations, which I've written here. So the t's are just fixed elements of the Lie algebra that obey the usual SU2 commutation relations. And you can check that this gives an explicit exact solution of the equations. And as I said, it has a singularity. It's singular at y equals 0. The commutation relations means that the t's are images of a standard basis of SU2 under a homomorphism from SU2 to G. Every such homomorphism leads to an interesting theory, but to get the Jones Polynomial and Khovanov Homology, we take rho to be a principal embedding in the sense of constant. Actually, there's been very little work on what one would get from other embeddings, I think. For G equals SU2, that just means that, see, if G is SU2, then G and SU2 are the same Lie algebra, and rho is just the identity map. If G is SUn, it means that the n-dimensional representation of G is irreducible under SU2. SU2 is embedded irreducibly. And this has an analog for every G. So although the theory is interesting for every rho, for the Jones Polynomial and Khovanov Homology, we take a maximally irreducible rho. I call this solution the non-pol solution because it was introduced by Werner Nahm around 1979 in his work on magnetic monopoles. That was in the context of Nahm's equations. So he was studying an ODE, but it was an ODE for 3 matrices. And his ODE was this. We're in 4 dimensions, but if we drop the dependence on 3 of the coordinates and also set some of the fields to 0, then our equations can be specialized to Nahm's equations. And this singular solution of Nahm's equations, precisely this one, was very important in Nahm's work. He didn't write it with the dxi because he didn't have the x's. He just said he had 3 matrices phi I. I mean, the way Nahm would have written it was just that phi I of y is ti over y. And he was on a half line with boundary or an interval, and then he would have similar singularities at both ends. And this kind of singularity was very important in what he did on monopoles.
Describe a monopole string in the 5-dimensional gauge theory?
Not quite, but I think I want to postpone more questions. So on R3 times R plus the non-pol boundary condition, just the boundary condition which I call the non-pol boundary condition, just says that a solution should be asymptotic to the non-pol solution for y going to 0. Now that was the non-pol boundary condition on R3, when the boundary is R3. But it has an elegant analog on any 3-manifold W. But to find that analog, you have to try to solve the equations in order 1. So the most singular term in order 1 over y is going to be the non-pol. But to get a sensible picture, you need to make sure you can say something sensible in order 1. And then beyond that, you get a sort of a straightforward formal expansion. So, and the term, I want to tell you the term of order 1. If the group is SU2, you take the G bundle E on which you're solving the equations. Well, the fancy way to say it is that it's the frame bundle of W, but what we'll use is that the corresponding adjoint bundle is the tangent bundle of W. Then you take A restricted to the boundary to be the Levi-Civita connection on the tangent bundle. With this choice of E, the formula makes sense. You can think of the numerator as stating that an isomorphism of add E with the tangent bundle. You see, dx's are maps with the dx would be a map from the tangent bundle to a number. So t dot dx is a map from the tangent bundle to the Lie algebra. So, but this map is the isomorphism, the identification of the tangent bundle with the Lie algebra. So, this for this formula to make sense, the E has to be chosen for SU2 so that the adjoint bundle is the tangent bundle. And then, if you take A to be the Levi-Civita connection on the tangent bundle, you can show that, sorry, I wrote the non-pol boundary condition, but I should have said the KW equations. It obeys the KW equations up to an error of order y, And the non-pole boundary condition simply says the solution should agree with this up to order y. You can generalize this to the case that the metric isn't a product near the boundary, but I just stated it for the product case. So I only stated this for SU2. But for any group, you take what I've just explained and embed it in the group using the principal embedding. And that's what the solution looks like up to terms of order y. Well, sorry. The non-pole boundary condition is the statement that the solution must look like that up to terms of order y. Now, showing that the non-pole boundary condition is elliptic is mostly an exercise in what Rafe Mazio calls uniformly degenerate elliptic operators. But you need to know some specific facts about the KW equations. The main thing you need to know is that if L is the linearization of the KW equations around the non-pole solution, then L as an operator between appropriate Hilbert spaces of functions on R4 plus has no kernel or co-kernel. It has closed range and no kernel and co-kernel. In particular, it's a Fredholm operator. And Fourier transforming is a step in proving this. And when you do that, you see that if there was a fifth dimension, it wouldn't have changed the argument. So if we spell this out a little bit more, the answer to your question would appear. Now, you actually don't have to check the co-kernel because another nice thing happens, which is that L dagger is conjugate to L by an explicit matrix. So it suffices to show that there's no kernel. One thing I'm hoping you'll believe by the end of this lecture is that a lot of nice things happen that make it easier than it might sound. So I'm pointing a few of them out when they come up, and this is one of them. Now, so we have to prove that the linearization has no kernel or co-kernel, but there's actually a nonlinear version of the statement that we proved. We proved that the only solution of the KW equations on the half space, R4 plus, in other words, R3 times a half line, which I call R4 plus, approaching the non-pole solution at y to 0 and also at infinity, is the non-pole solution. So that means that the complex associated to the empty link is of rank 1 and bigrading 0, 0. So that the Khovanov homology of the empty link is of rank 1 with the expected bigrading. Now, before trying to prove the vanishing results that we need, I want to get you in the right mood by explaining a simpler vanishing result that actually was in my paper with Kapustin for the KW equations on a 4-manifold without boundary. So that'll help us know what to try to do. So a lot of times, the way you prove that a differential equation doesn't have any solutions is by showing that some obvious inequality would be violated if it did. For example, if you want to show that there are no non-constant holomorphic functions, you might, on a Riemann surface, you might observe that if you square the expression d bar phi and integrate by parts, you could prove that that expression is strictly positive. That would be one way to prove that theorem. So in general, to prove such vanishing theorems, one often uses a kind of Weitzenbach formula. I can't help. This is going to be unintelligible. I tried to help the people who came in 2 or 3 minutes late. So, okay. Anyway, we have some equations, v equals w equals 0, where I've written them here. I've written here what v and w are. So anyway, I'll just help a little bit. We're doing gauge theory on a 4-manifold. Phi is a 1 form valued in the adjoint representation. And these are our equations. And we're going to practice by not quite proving there aren't any solutions, but by determining all the solutions. So clearly, the KW equations are equivalent to the vanishing of this expression. All I did was to take the sum of the squares of the equations. So it vanishes if and only if v and w vanish. And a short calculation reveals a formula for I, where I've assumed that m has no boundary. Otherwise, there would be boundary terms. For the moment, there won't be a boundary. And now you can see that this is a nice sum of positive things, except for a term involving the Ricci tensor. So if the Ricci tensor is non-negative, this would be a sum of non-negative terms. and we'd get a very strong constraint on possible solutions. That's good, but the condition that the Ricci tensor is non-negative is not satisfied for very many four manifolds. So what can you do if it's not true that the Ricci tensor is non-negative? Well, it's possible to say something useful even if the Ricci tensor is not non-negative, because it's possible to find a family of Weitzenbach formulas. So I'm now going to introduce the parameter t that I suppressed before. So I define self-dual and anti-self-dual two forms, v plus and v minus. If t is 1, these would be the self-dual and anti-self-dual parts of what I called v before. But we will now allow t to be any real number. And we don't change w. W is still what it was before. And I claim that these equations that v plus, v minus, and w are 0 are a one-parameter family of elliptic equations parameterized by Rp1. The way I've written it, it doesn't look like it's parameterized by Rp1 because the equations are singular if t is 0 or infinity. But by multiplying one of the equations by either t or t inverse, you can show that the family behaves well at both 0 and infinity. So it's really a family parameterized by Rp1. I'm sure that there's going to be some interesting monodromy around that circle eventually, but that hasn't happened yet, as far as I know. Now, okay, these are some other equations, so let's take the sum of their squares. And if you do that, you get a crazy formula. One term is the second Chern class times a function of t. And the other term is the same I that we had before. That's what's crazy. We're studying a family of equations that depend non-trivially on a parameter t, but the sum of the squares of the equations is independent of t modulo a topological invariant. So the same quantity I, to say it differently, what we're doing here, modulo a topological invariant, we've written I as a sum of squares. But because t is arbitrary, we've written the same object I as a sum of squares in many different ways. Almost, except for this topological invariant. So modulo topological invariant, which is a function of explicit function of t times p, where p is essentially the second Chern class, we've written I as a sum of squares in many different ways. And that has the following corollaries. First, if t is not 0 or infinity, the KW equations have no solutions unless p vanishes. If p isn't 0, then you look at the Weitzenbach formula with some value of t prime that makes j smaller than it is at t and reach a contradiction. Sorry, this should have been j times t. I'll show you why in a second. I've written it as if p is positive, but if p is negative, we would want the opposite inequality there. You see, suppose that p is not 0, and that we've solved the equations at some value of t. Well, solving the equations means the left-hand side is 0. Now let's change t. That doesn't change I. We can change t to make this smaller, unless it's 0. It can be 0 if the topological invariant vanishes. By not letting t be 0 or infinity, I've ensured that we're not at a maximum or minimum of this function. So we can make this function either bigger or smaller, and therefore, if p is not 0, we can make this expression smaller. So if we can make it smaller, keeping I fixed, we'd have to make the left-hand side negative, but the left-hand side is a sum of squares and started at 0. So the equations have no solutions for non-zero p. Now that we know that p is 0, we can drop this term, and we indeed have written the same quantity I as a sum of squares in many different ways. So therefore, if the equations are satisfied for one value of t, they're satisfied for all values of t. Because if they're satisfied for one value of t, then I vanishes, and therefore for any other value of t's, the sum of these squares vanishes, so they all vanish. So that's the second statement. If the KW equations are obeyed at one value of t other than 0 or infinity, then they're obeyed at all t. That's an immediate consequence, as I just explained, of the Weitzenbach formula once you know that p is 0. Now, knowing the equations are true for all t gives you a simple answer. then the equations can be written more simply by saying that if you form the complex connection A plus I phi, then it's flat. And it also obeys a kind of moment map condition, dA star phi equals 0. According to a theorem of Kevin-Corlett, the solutions correspond to homomorphisms from pi 1 of M to the complex Lie group that are in a certain sense semi-stable. So we were able to completely describe the solutions on a four manifold without boundary using one of the nice properties of this particular equation, which is that it has a whole family of Weitzenbach formulas. So the moral of the story is that the equations participate in many different Weitzenbach formulas, not just one, and it's important to know all of them. However, none of the formulas I've written down so far are useful for understanding the non-pole boundary condition. The reason is that if the boundary is non-zero, then the preceding formulas will have boundary contributions because we had to integrate by parts to prove those formulas. And those boundary contributions are divergent in the case of a solution with non-pole behavior along the boundary. Even without calculating, that's obvious, because the expression I called I in writing the Weitzenbach formula is divergent in the case of a solution with non-pole on the boundary. Let's just look at it, wherever it was. It was here. It was a sum of squares of a lot of things that behave badly. So phi is of order 1 over y, so this expression will be of order 1 over y to the fourth. Its integral dy has a cubic divergence. And this term is also cubically divergent, and it's all positive. So since I is plus infinity, since I is plus infinity when there's a non-pole boundary condition, but the formula will say that the sum of squares of the equations is I plus a boundary correction. For a solution, the left-hand side is 0, I is plus infinity, and the boundary correction, therefore, will be minus infinity in the case of a non-pole. So you can calculate the boundary condition, but even without you can calculate the boundary correction, but even without calculating it, it's clear that it will be minus infinity in the case of a non-pole. So if we're going to prove a vanishing theorem, we need a different Weitzenbach formula that won't have this problem. The best we could hope for would be a Weitzenbach formula on R4 plus, in which I is replaced by a sum of some other squares of some other quantities, whose vanishing should characterize the non-pole solution. So you can write down a whole list of quantities that vanish in the non-pole solution. What vanishes? Well, the curvature vanishes. There's one component of phi that we set to 0. There's no dy in this formula. So what I'll call phi y, which would have been the coefficient of dy, vanishes. So its covariant derivatives vanish, and commutators that involve it vanish. So these things vanish. And covariant derivatives in the x directions vanish, like these. And finally, Nam's equation was satisfied. So this is something else that vanishes. So there's a whole pile of things that vanish for the model solution, and it's easy to see that the vanishing of all those things characterizes the model solution. So we need what might sound like a miracle, that the sum of squares of all those things will be the sum of squares of our equations plus a boundary correction. And that's true. Define the sum of squares of the objects whose vanishing characterizes the non-pole solution as I prime. It's this. A useful Weitzenbach formula for the non-pole boundary condition will have to have I prime on the right-hand side. So the identity will have to say that the integral of v squared plus w squared should be I prime plus a boundary correction. In other words, if you take v squared plus w squared by integration by parts, you should be able to convert it into I prime with some terms you get on the boundary by integration by parts. And that's true. So delta is, I've written this as an integral at y equals 0, but actually delta is the sum of a contribution at the boundary at 0, but also on a large hemisphere at infinity. Now, to get a vanishing theorem that will say that the global non-pole solution is the only solution on the half space that obeys non-pole boundary conditions, we need to do the following. We need to prove that if A and phi approach the non-pole solution as y goes to 0 or at infinity, then they approach it fast enough so that delta equals 0. Let me give you an idea what's involved. So phi goes as 1 over y near 0. So f has to vanish near 0 faster than y to keep this term from contributing. And there's similar conditions for all the other terms that I haven't written. So we need to know something non-trivial about how rapidly the non-pole solution will be approached, if it is approached. But if we're able to show that anything that approaches the non-pole solution approaches it fast enough so that the boundary contribution is 0, then the Weitzenbach formula will say that a KW solution that satisfies the boundary condition must have I prime equals 0. And therefore, it must be the non-pole solution, because I prime was cooked up so that it only vanishes for the non-pole solution. Now, to find the expected behavior of a solution at 0 is a matter of looking at an ODE in which one ignores the x dependence, because that's non-singular. Our equation is schematically d by dy times 1 matrix plus something over y. Schematically, that's what our operator looks like when you linearize around the non-pole solution. In the x directions, you can Fourier transform, which was part of my answer to one of the questions. But this term is non-singular. The 1 over y term is singular, and that means that the d by dy term is singular. It scales as 1 over y. But this term doesn't affect the behavior near y equals 0. So you determine the expected behavior of a solution for y to 0 by looking at an ODE. So the ODE is just the linearization of Nom's equation, or more exactly, it's the linearization of a kind of doubled version of Nom's equation with a as well as phi. Half the linearized eigenvalues are negative and half are positive. The non-pole boundary condition amounts to setting to 0 the coefficients of perturbations with negative eigenvalues and allowing the positive ones. Then you check that the positive eigenvalues are large enough to ensure that delta is 0 when the non-pole boundary condition is obeyed. My explanation of this might sound slightly cavalier, but I think it's written up nicely in the paper, for which I credit my co-author. So this shows there's no contribution to delta from the boundary at y equals 0. To show there's no contribution at infinity, you do much the same thing, but now you have to look at the expected behavior on a large hemisphere at infinity. So now you look at the eigenvalues of the angular part of the linearized operator, which is an operator on a hemisphere with non-pole boundary conditions along the boundary. Again, just as with more conventional boundary conditions, there are positive and negative eigenvalues. The positive eigenvalues, well, I should better say the eigenvalues that vanish on the boundary of the hemisphere are such that there's no contribution to delta. So this leads to the nonlinear vanishing theorem. The global non-pole solution is the only solution on the half space that satisfies the boundary conditions. To show ellipticity, we actually wanted a linearized version of the same statement. The linearized version says that the operator L obtained by linearizing around the non-pole solution has trivial kernel. So it's actually not true that either one of those statements implies the other, but they can be proved in this context by much the same argument. Neither one trivially implies the other, but they can be proved in similar ways. So together with the general machinery of uniformly degenerate elliptic operators, this leads to the ellipticity of the non-pole boundary condition in the absence of knots. But what are we supposed to say in the presence of knots? That's one question. Another question is how much time I have, because I'm going a little bit too slowly. I'll try to do it in 10 minutes. So for this, we considered the case that the knot is locally a straight line in R3. So we work on R4 plus with the knot that lives on a straight line in the boundary. So here's the picture. Here's R3 schematically. Here's R plus. And any knot looks locally like a straight line. So the basic case is to understand first the case of a straight line. The idea is going to be to find a singular model solution in the presence of the knot. The solution will coincide with the non-pole solution near a boundary point away from K, but it will look different near a point of K. The model solution will depend on the choice of an irreducible representation of the dual group. Then a boundary condition is defined by saying one only allows solutions of the KW equations that look like the model solution near the knot. For this to make sense, the model solution must look the same near any point of K. So we assume that the model solution is invariant under translations along K. So we reduce to equations on R2 times R plus with the knot now represented by a point in the boundary. So there's a slightly simpler picture. We're in 3 dimensions, and something funny happens at one boundary point. Once we reduce to 3 dimensions, the KW equations become tractable. So first of all, you can motivate setting phi y to 0 by a Weitzenbach formula. I'd say motivate it rather than prove it, because you have to understand the boundary conditions before you could prove anything. So I prefer to say that if you study the potential Weitzenbach formulas, you see it's logical to expect that your model solution will have phi y equals 0 and a1 equals 0. And then the KW equations become tractable. So I'll assume that x1 runs along the knot, x2 and x3 parameterize the normal plane to the knot, and y measures the distance from the boundary. Then you do something very funny. You introduce 3 differential operators, 2 of which are of degree 1 and 1 is of degree 0, and also a moment map. And the KW equations in this situation say that the operators commute and the moment map vanishes. These equations are a hybrid of 3 much-studied equations in the mathematics of gauge theory. If you drop D1 by considering solutions where nothing depends on x2 and x3 and a2 and a3 are 0, if a2 and a3 are 0 and fields are independent of x2 and x3, then D1 is effectively 0 and you can drop it. And I'll mean something similar by dropping the others. If you drop D1, you get Nom's equations. If you drop D2, you get Hitchin's equation. And if you drop D3, you get the Bogomolny equation. So 3 much-studied equations of mathematical physics in dimensions 1, 2, and 3 are specializations where you drop one of the Ds.
Independent of x1?
By definition, yes. We assume things are independent of x1 to reduce to 3 dimensions before being able to put the equations in this form. Now, the full system of equations is tractable for the same reason each of the 3 specializations is. The equations that the operators commute are invariant under complex-valued gauge transformations. And the combination of setting mu to 0 and dividing by unitary gauge transformations is the same as forgetting about mu and dividing by complex-valued gauge transformations. Usually that's only true for stable solutions, but here, because of the boundary condition, all solutions are stable. So the moduli space of solutions can be understood in terms of complex data. I won't have time to explain the details, which involve O pairs and lead to familiar integrable systems. Moduli space is a term of art because generally the moduli spaces consist of finite sets of points, which can be interpreted in holomorphic terms. I'm cutting some corners in these statements. The full system of equations, without forgetting about the non-pole, this combined system describes Hecke modifications of Higgs bundles in the sense of geometric Langlands. In geometric Langlands, people usually consider Hecke modifications of bundles, but this is a set of equations that can be used to describe Hecke modifications of Higgs bundles. Spaces of Hecke modifications have been discussed in relation to Khovanov homology by several authors. Usually this is done in a B model formulation that does not have manifest symmetry, or an A model that lacks the Q grading needed to get a satisfactory account of the Jones Polynomial and Khovanov homology, and which will sometimes also lack manifest symmetry depending on what you try to do. The point in what I'm describing is to achieve the symmetry with the full Z times Z grading. But this requires the peculiar non-pole boundary condition with the Hecke modifications made only in the boundary. So Kamnitzer had a paper on a hypothetical A model, but his Hecke modifications were made away from the boundary, if you express it in the language I'm using. And that would lose you the second Z grading. Now, another reasonable thing to expect is that the model solution should possess the symmetries of the knot. Remember, the knot was just a straight line, and there are two symmetries, rotations around the knot. So rotations of the three-dimensional boundary around the knot is a symmetry, and also scaling of all four dimensions, keeping the knot fixed, is a symmetry. You could express it in three-dimensional terms. Well, I express it here in three-dimensional terms. You rotate the boundary R2 around the point where the knot lives, and you also make a rescaling of R2 times R plus, keeping P fixed. If you assume that the model solution should have those symmetries, then the equations reduce to affine Toto equations, which are integrable, and you can find all the solutions. You find all the solutions in the enclosed form, and the solutions consistent with the non-pole boundary condition away from the knot are indeed classified, as I've been promising, by an irreducible representation of the dual group. I found these solutions for SO3 in my paper, and my student Viktor Mikhailov found them for general G somewhat later, using the integrability of the affine Toto equation. Now, how would we go about proving that the KW equations with the boundary condition defined by one of these model equations is a well-opposed elliptic problem? Basically, modulo generalities, you need to show that the operator L obtained by linearizing around one of them has no kernel or co-kernel. It's again sufficient to show that the kernel vanishes. Just as in the absence of a knot, there's actually a nonlinear analog of the vanishing of the kernel. The nonlinear analog says that any solution of the KW equations, asymptotic to the model solution, in the presence of one infinite straight line, actually coincides with the model solution. That's one version. I think there are a few other versions with several parallel straight lines. The vanishing results we want are the sort that often follow from a Weitzenbach formula. But what will the Weitzenbach formula have to be? None of the formulas I've told you about so far are well adapted to the presence of a knot. For example, even the more subtle one that works with a non-pole away from a knot is not useful in the presence of a knot, because I prime is divergent in the presence of the knot. So I prime will be plus infinity, and hence delta will be minus infinity with a knot present. As soon as you have that kind of cancellation, you can't learn anything from a Weitzenbach formula. We need to make a further improvement in our Weitzenbach formula to include the knot. We need a new Weitzenbach formula, but we find it by imitating what we did before. We find a collection of quantities xi whose vanishing characterizes the model solution. So the xi are more or less obvious. So some of them are real and imaginary parts of the equations. They vanish in the model solution. And the other are the quantities that vanish because the model solution has a1 equals phi y equals 0. So there are a lot of obvious quantities that vanish in the model solution, and their vanishing characterizes it. So you define I double prime to be the sum of squares of all the quantities whose vanishing characterizes the model solution. And now, what we need to be true is that the sum of squares of the equations we're really studying equals I double prime plus a new boundary term, meaning you should be able to prove yet another crazy-looking identity by integrating by parts. But, of course, it's true. You still need to show that delta hat is 0, that the new boundary term, delta hat, is 0 in the case of a solution that obeys the KW equations and is asymptotic near the knot to the model solution, and also at infinity. For this, you need to know what's the asymptotic behavior near the boundary and at infinity of a solution of the KW equations. We already know the behavior at a generic boundary point, which was used in our proof of the well-opposedness without a knot. To find the behavior at the knot and also near the knot and also at infinity, we now need to solve the angular part of the linearized equation on a 2D hemisphere that looks like this. So there's a boundary point, and I draw a little 2D hemisphere around it. If it's a small, so because the model solution is scale invariant, the linearized solutions have definite scaling behavior. But the scaling exponents are determined by eigenvalues of an elliptic operator on the hemisphere. So you have to analyze the spectrum of a certain elliptic operator on the hemisphere and find that its eigenvalues have favorable properties. It turns out that the eigenvalues are favorable, so there's no contribution of delta hat. You're either the origin or infinity. So this fact, together with the relevant Weitzenbach formula, imply that a solution of the KW equations in R3 times R plus that's asymptotic everywhere to the model solution with the knot actually coincides with that model solution. A linearized version of the same argument shows what we actually need for ellipticity, that the kernel of L vanishes. So much the same argument. This is a funny case where the nonlinear version is easier to explain, but it also has a linearized version. That's the main step in showing that L is a Fredholm operator in the presence of an arbitrary knot K embedded in any 3 manifold W. There are still some details needed to show that this gives an elliptic boundary condition for the nonlinear KW equations, which is why the second paper hasn't quite appeared yet. Thank you.
Questions?
Is there a realization of a scheme relation in terms of boundary conditions? I suppose you want to...
So I think your question might be, the Jones polynomial, for example, can be characterized by skein relations. Can you explain from this point of view why skein relations are true?
Right.
So to physicists, there's an a priori explanation. It has to be true. But as a mathematician not understanding that, you'd like to know if there's a direct computation showing it's true. So David Agayoto and I did a lot of that about 3 years ago in a paper I cited earlier. We did deduce the Jones representations of the braid group from this picture. And with a little bit less precision. We need a little bit more than that to get the Jones polynomial. What we really did most fully, well, as a mathematician, you'd ask many questions about our analysis. But still, you'd find that there was a pretty clear outline of what you'd want to understand. So what we did most fully was to explain how this picture leads to the Jones representations of the braid group. A little bit less fully, how it leads to the Jones polynomial. I assume that's a reasonable approximation to answer your question, which was specifically about the skein relation. The skein relation, after all, is part of the story about the braid representations. So I think what I said was really more general, even though I didn't answer you directly. You had a question.
Yeah. So you said that you could see the invariance, assuming all the analytic issues are resolved.
Yes.
You could see the invariance of the Jones polynomial.
Yeah.
Somehow by pure thought, because everything's elliptic and the modular.
Because the counting of elliptic, the same reason that the Donaldson invariants are invariants. Because the counting of elliptic of solutions, let me just repeat it for everyone else. Because the counting of solutions of an elliptic differential operator is invariant under continuous variations of parameters, given a few general properties.
So then in the second thing, you built the chain, a bi-graded chain complex.
Yes.
And so the usual story with Khovanov homology is that only the homology of that complex is an invariant. But
only the homology was an invariant.
Yeah, but so why isn't it? I mean, again, you were counting solutions of some elliptic operators. So why is it not now the case?
Because we're not on a compact space, really. It's because time was infinite. So the basic example of your question is in Morse theory. Suppose let's take a manifold with a Morse function. So one problem is to count with signs its critical points, where the sign will be -1 to the Morse index. Then we could decide to categorify that problem by passing to the solutions of the flow equation, the gradient flow equation. And your question now arises because the complex that computes the cohomology is not invariant. And the resolution is actually very well known. As you make a one-parameter family, it depends in an essential way on the fact that R is not compact. As you make a one-parameter family, a solution can split up into two widely separated bits. So the statement that the counting of solutions is invariant will be true in physics language if nothing bad can happen at short distances, long distances, or large fields. So The long distances is the phenomenon that occurs in Morse theory, which you're essentially asking about. It's related to what people in fields like Morse theory and fork homology call broken trajectories. The short distances has to do, in Donaldson theory, there's bubbling. But here I essentially prove for you there's no bubbling because I showed that on a compact form manifold there was no solutions at all. Well, there are solutions corresponding to flat connections, but locally they're completely trivial. Okay. You should worry about large fields, and a little bit of investigation will show that it helps there if the Ricci tensor is non-negative. So you ask a good question, and the answer has to do with the infinite volume of R. So I didn't attempt in the lecture to explain exactly what are the general properties that are needed to make the counting of solutions a topological invariant. But there is a general story, and in my opinion, there are excellent reasons to believe it is all true in this example. Examples where it is true tend to be relatively few and to have a lot of impact in mathematics. Yes?
I want to ask you different questions.
Yes.
So you mentioned the A model a couple of times.
I call what I've done an A model.
Just could you translate to the conventional language of the A model? What would be the worksheet and what is the target space of the model? Or just the
I can.
word wide?
No, it's, well, first of all, I can make it precise, but before making it precise, let's just say it philosophically. So philosophically, the A model is a world where you count solutions. And the B model involves periods and other funny things. But I'm a little bit worried about the time if I try to give a detailed answer. So what did you say?
When is the next talk?
Well, but people need a break.
Okay. No,
I want to give a very schematic answer. I'm not going to give a detailed technical answer. In the sky, this started with M5 branes. And to simplify slightly, the M5 branes were in a product of R2 with a product of 2 manifold. R2 could be any sigma, any 2 manifold. But then there's a product of 2 manifolds. Well, sorry. I'm just going to call them sigma 1 and sigma 2. This can be topologically twisted in a way that gives a 2-2 model in 2 dimensions. The exchange of the 2 factors is a mirror symmetry. And my description is related to other descriptions I see in the literature by that mirror symmetry. So mine is an A model, and the other is a mirror B model.
For key factors.